Welcome once again to a time value of money video, and this is our fourth time value of money video, and I'd like to talk now about a present value interest factor for an annuity, and it is a function of R, the opportunity rate of return, as well as N, the number of cash flows in the annuity. As a reminder, an annuity is a cash flow stream that is characterized by three criteria. The first is their equal-sized cash flows. The second criteria is that the interval between the cash flows is fixed, or you could say is a constant. And three, there are a finite number of these cash flows. Finite number of cash flows. And if all these three are true, then we have an annuity. The interval between the cash flows can be a minute, a day, a week, a month, a year, whatever you like. Okay, we'll call the interval between cash flows a period, or maybe 2 periods or 3 periods, just so the interval between the cash flows is fixed. What I mean by that is you could say, hey, I get a cash flow every year on the first day of the year. But another way of describing that is you get a cash flow every 12 months. And so you'd have 11 empty months and then a 12th month where you get a cash flow. So that's what I meant by that last fact. Okay? So, the present value interest factor for an annuity, we can think of as being a sum of present value interest factors. This is just a sloppy little statement, but it's true. Kind of notational, not really mathematical, notational. And here's what I mean. Suppose we've got this cash flow stream that looks like this. Date 0, date 1, date 2, and date 3. And we have $100, maybe $100 million, whatever you want to think of. Just 100 coming due to us at date 1, date 2, and date 3. Maybe we won a lottery that pays $100 million, but it's kind of a cruel lottery in that it doesn't begin paying for one whole period. Okay, and the idea is we're interested in trying to figure out what the value of this annuity is as of date 0. What's it worth now? So in order to do that, we need to identify the appropriate opportunity rate of return. The appropriate opportunity rate of return. It's the rate of return that is your next best use of funds rate. Okay? And so in this case, the opportunity rate of return, since we're going back in time, trying to value each of these individual cash flows at a point earlier than the time in which the cash flow occurs, we call this opportunity rate of return, in this case, a discount rate. Okay, so the discount rate is our opportunity rate of return in this example, okay, because we're moving back in time. Well, if we're after the date 0 value here, here's how we do it. A simple way is just to work with the individual cash flows. Now, you learned from my first time value of money video that In order to move a single value back in time, we use a PVIF. So the date 0 value here of that date 1 cash flow of $100 is, so if what I'm after here is the present value of this annuity. Okay, and so now I got this $100, so that $100 multiplied by a present value interest factor, where we have our value of R, let's just say that's 10%, 0.1 decimal equivalent. And N, well, N for a PVIF means the number of periods you're moving back in time, so the N here is just 1. Okay, that's going to give us the value of this $100, but this annuity has 3 cash flows, so what about this one? Well, this one has to move back in time 2 periods, so to this I will add this $100 right here, multiplied by its own PVIF, and that, in this case, R is still 0.1 per period, but N is 2 because we're moving 2 periods back in time. And then to that I will add that third $100, paying at date 3. That has to move back 1, 2, 3 periods to get to date 0. So there's that 100. Multiply it by its PVIF, where R is still 0.1 per period, but now N is 3 because we're moving back 3 periods in time. So this would be written like this. It would be equals 100 times 1 over 1.1 to the first power plus 100 times 1 over 1.1 squared plus 100 times 1 over 1.1 cubed. Okay, and then here circled in red are our present value interest factors. Well, the next thing we'll do is we will factor out, we will factor out the 100. Oh boy, I don't know what I did there. I'm dangerous with these things. There we go. So I will now factor out the 100. And of course, I will factor it out using green. Why not? So then my next line here becomes the present value of the annuity equals 100. And then in parentheses, I'll have 1 over 1.1 plus 1 over 1.1 squared plus 1 over 1.1 cubed. And we see here that we have, that's the ACF, the annuity cash flow. And here we have a sum of PVIFs. Okay, a sum of PVIFs. Try to write a little neater here. Okay, and then now I can get kind of specific. Now I'm going to say we have this application formula. This is application formula number 4, by the way. I'll have a table coming up for you later. Present value of the annuity is equal to the annuity cash flow times a present value interest factor for an annuity. In this case, well, it's always a function of R and N, but in this case, our R is equal to 0.1, and our N is equal to 3. Why 3? Because for a PVIFA, the N value represents the value, represents the number of cash flows in the annuity. And we obviously have 3 cash flows in this annuity. Okay, so there we go. And this is the kind of the general formula. Well, the PVIFA can be thought of, remember this PVIFA right here that we're talking about. This PVIFA right here, okay, is this right here. And that's the point, that when we did it using individual PVIFs, the logic left us with the observation that, my goodness, that sum of PVIFs right there has to be the PVIFA. And indeed it is. So we can say that a PVIFA is equal to the sum for I equals 1 to n of 1 over 1 plus r to the I power. If we expand the summation when we have r is 0.1 and n is 3, so then this would become the sum for I equals 1 to 3 of 1 over 1.1 to the I, and of course that will be equal to 1 over 1.1 to the first power, because we start with I equal to 1. Okay, and then we wrote the entire term, plugging in 1 for the I, and now we're done. So we put a plus sign because this is obviously a summation, right? We're adding. If instead of having that sigma, if we happen to have a pi, that would mean multiply the terms. But we're adding. We have the sigma. Okay, so back to this. We've got 1 over 1.1 to the first power. Now the default step size is 1, so I now becomes 2 because we finished the first term, ready for the next term, and the default step size is 1, so I was 1, now it's 2, so I only appears right there, so it's 1 over 1.1 squared. We're done. Add the next term, now I is 3. Oh, this is our final term, so 1 over 1.1 cubed. And so that's another way of seeing what the PVIFA is, a sum of PVIFs, but not this just general notational observation from back here, but now more specific. It's this. This is what the PVIFA is. And there's our example. Now, so we see then that if in our prior example, the present value of the annuity at date 0 would be equal to 100 times the sum of these 3 numbers. And the sum of those 3 numbers is, right now I'll just call it PVIFA. Okay, so the present value of the annuity, which is measured in dollars, is equal to the annuity cash flow, which is $100, times the PVIFA. Okay, and well, I wonder, what if we had a cash flow stream that involved 360 payments? For example, the number of payments specified in a typical 30-year loan contract, maybe a mortgage on a house. Well, this could be a very cumbersome because we'd have a lot more terms. Well, I just wonder if there's a computational formula that we could use. And it ends up there is. So let's now see how it comes into being, how we get, well, I'll tell you what the computational formula is. It's 1 minus 1 over 1 plus r to the nth all over r. That is the computational formula. That's it. That is the computational formula for the PVIFA. Okay, big question. Why? Why is that it? Where did it come from? Well, let's see. We're going to use logic identical to the logic we used when we were proving what the FVIFA computational formula was in the last video. So we start off by saying, okay, here's a definitional equation. We would put a little s for sum, but we've named our sum. Our sum is PVIFA. So I'll say PVIFA equals, and this is the general case. So it equals 1 over 1 plus r plus 1 over 1 plus r squared plus 1 over 1 plus r cubed. I go plus dot 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 plus last term 1 over 1 plus r to the nth power. Last term. I guess this sort of presumes that it's at least, 4 or 5 terms, but this is just the general way of writing it. Okay, so that's the PVIFA. It's a sum of PVIFs, and here I have the general case. Okay, well, again, keep your eye on the ball, so to speak. What we're trying to do is prove where that came from. And so we have a definitional equation. Now I'll create a new equation called Roman numeral 2. And what I'm going to do here is I'm going to multiply both sides of the equation by 1 plus r. And so on the left-hand side, I'll have 1 plus r times PVIFA. And on the right-hand side, I'll have 1 plus r over 1 plus r. Then I have 1 plus r over 1 plus r squared. Then I'll have 1 plus r over 1 plus r cubed. And then plus dot 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 plus 1 over 1 plus r. 1 plus r. Oops. Sorry. 1 plus r over 1 plus r to the n. Okay, just multiplied every term by 1 plus r on both sides of the equation. Okay. Well, let's see what we have. Over here we've got 1 plus r times PVIFA. Over here, well, the first term is 1, and the second term ends up being 1 over 1 plus r. And this term right here becomes 1 over 1 plus r squared. And then we have plus dot 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 plus, and this last term becomes 1 over 1 plus r to the n minus 1. 1 over 1 plus r to the n minus 1. Okay, fine. That's what we have. And this is equation 2. Okay, so now logic comes into play now. And I like to say, if the left-hand side of equation 1 equals the right-hand side of equation 1, which it does, because it's a definitional equation, then when we multiply both sides of the equation by the same value, logic tells us that this still equals this. Okay, no problem there. That's why we have that equal sign. But now here comes the logic. That implies that the difference in the left-hand side of the equation, if I subtract, say, this from this, has to equal the difference in the right-hand side of the equations. Okay. Okay. So let's see what happens. Well, if I subtract this from this on the right-hand side, and again, if I subtract this from this on the left-hand side. Well, on the left-hand side, I'm going to have 1 plus r times PVIFA minus PVIFA. On the right-hand side, let's see what we have. Well, here I have a 1. And there's no 1 up here, so I'm just going to say, okay, it's kind of like 1 minus 0. Okay, and then that stands. And then I've got, down here I have this term, and up here I have the same term. And remember, it's this minus this, so this minus this, they cancel out. And then I look at my next term. This is 1 over 1 plus r squared, but that's up here also, and it's this minus this, so they cancel out. And I think you'd agree that the next term here would be this one, so that would cancel with whatever's next. And then you'd agree, I think, that this term right here, 1 over 1 plus r to the n minus 1, would cancel out with the term that precedes this term. So I'll kind of put a little line right there. And that means the last thing is kind of 0, I mean nothing there, minus this last term right here. Okay, this change the color here. This term right here. So I'm going to have 1 minus 1 over 1 plus r to the n. Just logic. Again, the logic was if this equals this and this equals this, then the difference in this and this has to logically equal the difference in this and this. And that's what we're left with here. So now let me distribute the PVIFA over 1 plus r. So I'm going to have 1 times PVIFA is PVIFA plus r times PVIFA minus PVIFA equals 1 minus 1 over 1 plus r to the nth power. They cancel, so I'm left with r times PVIFA equaling 1 minus 1 over 1 plus r to the nth. And then therefore, PVIFA, we're getting what we're after. Here's what the PVIFA equals. 1 minus 1 over 1 plus r to the nth power all over r. So there we go. And we've proved what we wanted to prove. Okay. That is indeed equal to that. So that's a proof of a PVIFA. And some things to remember about the PVIFA again are the interpretation of N for the PVIFA is number of cash flows in the annuity. Okay. And as is the case, as you will see is the case with all of our multiple cash flow stream present value interest factors. This is our first multiple cash flow stream present value interest factor. But all of them will give us the value one period prior to the first cash flow of the annuity stream, of the annuity. So this analysis that we're doing will always give us the value of that annuity one period prior to the first cash flow of the annuity. And you can see why that's the case, because up here, when we broke out the terms initially using the old-fashioned way, we took them back to date 0, and just the way we built it with this value right here went back 1 period, this went back 2 periods, and this went back 3 periods. They were all going to date 0, so we valued them all at date 0, which is 1 period prior to the first cash flow of the annuity. So we built our PVIFA to be like this. So make sure you remember this very important point here. Okay, we calculate the value of the annuity. Okay, we calculate the value of the annuity as of, and then right there, 1 period prior to the first cash flow of the annuity. That's what we did. It's very important that you know that. Now notice what it says, 1 period prior to the first cash flow. So if I'm asking, or if you're being asked, or if you're just calculating, the value of, let's say, an annuity paying $2 million at each of days 1, 2, 3, and 4, if you're being asked to calculate the value of this annuity at date 0, then here the present value of this annuity would be annuity cash flow times the PVIFA. We'll assume R is still 0.1, but now N, the number of cash flows in the annuity, is 4. It's 4 because this is just a different example, right? So, all right, so that's what we have. And it's going to give us the value when we use this PVIFA, which of course will be 1. This PVIFA here will be 1 minus 1 over 1.1 to the 4th power over 0.1. And it's going to give us the value 1 period prior to the first cash flow, which is right there. Now, let's suppose that instead of the annuity starting at date 1, let's assume the annuity started at date 5. So this annuity paid at dates 5, 6, 7, and 8. No cash flows before that, $2. Then when we did this analysis right here, it would give us the value of the annuity, same formula, 1 period prior to the first cash flow. So 1 period prior to that first cash flow, in this case, would be date 4. So, in other words, $2, which is the annuity cash flow, times the PVIFA, where R is 0.1 and N is 4, it would be 2 times 1 minus 1 over 1.1 to the 4th power over 0.1. Okay, so put this sign there, and that's going to give us the value at date 4, because 1 period prior to the first cash flow in the annuity is date 4. So what we have to remember is, in this case, if you, for some reason, are asked to find the date 0 value, okay, that you would then have to do a second step. At this point right here, we have the annuity characterized as a single dollar value, okay, just as of date 4. So in solving for the date 0 value, what we do is we'd have to take the date, so the value at date 0 would be the value at date 4, which is, again, this, multiplied by a present value interest factor. We'll assume our opportunity rate of return is still 10% per period. And then how many periods do we have to go back in time to go from 4 to 0? Well, obviously it's 3, 2, 1, 0. We have to go back 4 periods. So this PVIF will be R equals 0.1, N equals 4. Remember, the meaning of N for a PVIF is the number of periods we're moving back in time. Just as a reminder, the meaning of N for a PVIFA is the number of cash flows in the annuity, just as the meaning of N in an FVIFA formula was also the number of cash flows in the annuity. So in this case, the value at date 0 would be 2 times 1 minus 1 over 1.1 to the 4th, all over 0.1. So up, I just noticed something. Up here, this should be a multiply sign. Make sure that's a multiply sign in your notes. I put a plus there. That's a multiply. I know I said multiply, but that's a multiply. Okay, so it's this times this PVIF, which is 1 over 1.1 to the 4th power. And when you do the arithmetic here, you get the value of that at date 0. So again, the important thing to remember here is with a PVIFA, it always gives us the value 1 period prior to the first cash flow of the annuity. And in the second case, we saw that 1 period prior was at date 4. It was the same formula giving us the value 1 period prior. If for some reason in the second case they want the value at date 0, then you have to multiply by a separate term to get that. It's very important that you realize that. And at this point, let me just summarize via a little table what we've learned so far. I'll make a little table here. IF stands for interest factor, and then I'll have computational formula, and then I'll have application formula. Okay. So let's see what we got. Interest factor. The first one we did was do these in red. Future value interest factor. The computational formula was 1 plus r to the nth power. And the application formula was future value equals present value times future value interest factor. Okay, that's number 1. Number 2 was present value interest factor, and that computational formula is 1 over 1 plus r to the nth power, and the application formula was present value equals future value times the PVIF. The third interest factor was the FVIFA, and the application formula was 1 plus r to the nth power minus 1 over r, and the application formula was future value of annuity equals annuity cash flow times future value interest factor for the annuity. Okay, and then the one we just learned in this video, the interest factor was the present value interest factor for an annuity, and so PVIFA, and the application formula, the computational formula is 1 minus 1 over 1 plus r to the nth power over r. Just put that in a little rectangle. And then the application formula is present value of the annuity equals annuity cash flow times PVIFA. PVIFA. Let me just erase that and make it nice and neat. Oops. There we go. And so there's a little table for you to have. Now we're going to have more interest factors. 4 more we'll talk about. I think this is enough for this video. Thanks for watching.